Hello, I'm Brian Wheatman. I'm going to talk about overcoming the point range query trade-off for in-memory B trees. This is work I did along with Helen Shu, Amanda Lee, Manoj Maneri, and Prashant Pandey. B trees are a classical indexing data structure. They are a tree with B minus 1 pivots at each node, giving B children. This gives a tree with height log base B of n that can perform all different point operations in time O of log base B of n. They are used all over computer science, from in-memory indexing to databases to file systems, and they are asymptotically optimal for point operations. B-trees have a trade-off between the performance of inserts and that of long-range queries. These range queries are used in real-time analytics for filtering and aggregates, and in graph processing for iterating over the neighbors of vertices. On this plot, we see the self-relative performance of inserts, finds, and range queries as we vary the node size. The node sizes can be found on the x-axis, while the y-axis shows how close to the best performance that node has achieved. In this experiment, we take a structure with 100 million elements, and time inserting 100 million new random elements, time querying for 1 million elements that exist in the structure, and time performing 1 million range queries of average length 50K. We find that the larger nodes are able to reasonably substantially increase the performance of range queries at the cost of the performance of inserts. Here's a look at the high-level results. We evaluate our structure, the BP tree, on several tests from the Yahoo Cloud Serving Benchmark, YCSB, and compare it to a selection of different structures. We compare it to a standard B+ tree based on the TLX library that we added optimistic concurrency to as a baseline, as well as mass-tree and OpenBW tree from the literature. We find that the BP tree always performs at least the second best and greatly exceeds existing work on long-range operations. Let's zoom in a bit more to this trade-off. Here we have the insert throughput on the x-axis and the range query throughput on the y-axis. On this plot, up and to the right is an improvement in performance. And the different marks are the different node sizes. The first thing that we can see is 2 to the 10 dominates smaller node sizes because it gives better insert and range query performance. However, after that, we see that we are continuing to increase the range query performance. However, we are decreasing the performance of inserts. And so this point over here, 2 to the 10, was the case shown before for the YCSB benchmarks. And this point up here is the best for range queries, getting over a 2x speedup. However, the price of that speedup is a 16x slowdown for inserts. Now let's think about why increasing the size of our nodes can increase our range query performance. So if we have a small node, and want to perform a range operation that iterates over multiple different nodes, what we will find is after we operate on a few elements, we then need to follow a pointer to operate on elements in the next node. However, each time we access a new node, we will get a new random access, and these random accesses can be expensive. However, if we're operating on larger nodes, then we're going to reduce the number of these random accesses by the amount that we increase the size of our nodes. However, if we make our nodes larger, this requires more work on inserts. Traditionally, B trees will use sorted arrays to maintain the elements inside the nodes. And so if we want to insert a new element somewhere inside the node, we need to shift over all of the elements to make room for that element. And if we have a small node, we don't need to shift over that many elements. However, if we increase the size of the nodes, we also increase the size of this shift. So if we look again at our trade-off, the question is, can we improve it? Can we get up and to the right? And based on the fact that I'm giving this talk, as you might be able to guess, the answer is yes. Yes, we can do up and to the right, and that's what I'm here to talk about today. Our BP tree, which gives us this new trade-off curve, which enables us to increase insert performance by about 5%, and also increase our range query performance by 50%. So how do we do this? We do this by introducing a new buffered partition array for use in the leaves. The idea of this is to collapse the bottom 2 levels of the B tree into a single, larger, insert-optimized data structure. That's optimized both for inserts. However, because it is a single array, single memory block data structure, it also gives us good range query performance. So the first part of the BPA is the log. The log simply stores the last couple inserts to make individual insertions efficient, and then we flush the log only when empty. When an element is inserted to the log, we don't need to check if it already exists in the structure. We do allow a duplicate both in the log and in the structure. The next is the header. You can think of the header as basically the second from the bottom level in the B tree. This will enable faster searches of the rest of the structure because it will narrow down the region. Last, we have the blocks. The blocks are going to store continuous subranges of the structure, sort of like the leaf nodes of a standard B tree. Also, we do store these blocks unsorted to reduce shifting of elements around during inserts. So let's walk through a few example insertions in the BPA. First, let's insert 22. When we insert 22, we can just stick it in the log. This makes inserting 22 very efficient. I will also note here that the log elements are not sorted, again, making these inserts very efficient. Next, let's insert 27. When we insert 27, we find that we now have a full log, and so we will want to flush the log. And so, when we flush the log, we're going to start by sorting it and counting how many elements are destined for each block. So in this case, the 8 will end up in the first block. However, it's already there, so it won't add anything. And then the remainder elements will end up in the third block. However, this will overflow that block. And because that block gets overflowed, we need to sort and redistribute all of the elements evenly amongst all of the blocks. And so we can perform that. And now we see that all of our blocks are as even as possible, and all of our blocks are sorted. Now let's go over a range query. Here, we're going to do a sorted range query, starting at element 7 and doing a length of 2. So we're going to do this with a two-finger merge between the log and the remainder of the structure. So we start by sorting both the log and the first relevant block. So here we have sorted the log and it is now in sorted order, 8 and then 25, and we've also sorted the first block, and so it is also in order, 8 and then 13, and then we're going to perform a two-finger log with the log and the block pointer. So we first deal with 7, and now we have both the log pointer and the block pointer pointing at the same element, 8. Now we do know that whatever element that is in the log is more recent than the element in the block, so we will take that one and we will skip over the one in the blocks. So what has this achieved? Now let's take a look at the performance of both the B tree and the B plus tree as we vary the leaf size. We find that exactly as we'd hoped, the BP tree is able to maintain its efficient inserts as these nodes get much bigger, which enables us to use these much larger nodes to improve our range query performance. While I will note that the B plus tree with these extremely large nodes does better than the BP tree, it is not possible to use those very large nodes with the B plus tree without suffering the very slow insert performance. In this experiment, we're testing both long scans with an average length of 50,000 elements and short scans, which have an average length of 50. And for short scans, these are often scans that are inside of a single node in the tree, and thus there's no benefit of using the BP, and the B plus tree is able to be slightly more efficient based on being simpler. So one thing we noticed is just how big these nodes got before the range query performance started to level out. In fact, here we're going up to 64 kilobyte nodes, which is much bigger than traditional node sizes in B trees that might go up to 256 bytes or so. So why is it the case that these very large nodes do give us such a benefit? So first, let's think about the classical DAM model for measuring the cost of memory accesses. Here, we're going to have a sort of large infinite memory that we can fetch data on and bring it to our small memory for processing. So here, every time we want to bring some block of data from our memory, from a large memory to our small memory for processing, it's just going to have unit cost. So here we're going to bring data one at a time, And so here, bringing 5 blocks of data is going to have a total cost of 5. However, a more recent model, the affine model, attempts to account for sequential block accesses being faster than random. You can think of this like for old spinning disks. When you want to read something off the disk, you first need to perform a disk seek, find where on the disk you need, and then read it off. And so if you then read 2 things sequentially, you only need to perform the seek once. So in this case, as you're accessing the blocks, the first couple blocks are sort of randomly spread out and will all have unit cost. However, after that, you will access these sequential memory blocks, and these will be cheaper to access. So we call this 3 plus 2 alpha, 3 for the random, and alpha as some number smaller than 1 that corresponds to how much cheaper it is to read the sequential block access versus the random. We found that the affine model holds true for RAM as well. We tested this by timing how long it takes to read 8 gigs of data when reading it in randomly ordered chunks of various sizes in parallel. This plot shows time on the y-axis and block size on the x-axis. We see the empirical result in blue, an estimate from the DAM model in green, and the estimate from the affine model in red. We find that we see considerable speed up, both after we hit 64 bytes for the cache line size, or even 4 kilobytes, the page size. We find that our system had an alpha of about 0.3. So going back to the YCSB benchmarks, specifically, we ran 4 different workloads from the original YCSB benchmarks, which varied the frequency of inserts, finds, and short-range queries. And by short-range queries, I mean those with average length of 50%. Across all of these, we find that the BP tree is consistently the second best, only being a couple percentage points behind the best. We also added 2 new workloads that specifically were designed to stress these long scans that we optimized for. The first is a sorted iteration. These will perform a range query of sorted data of average length of about 5K. The next was an unsorted operation, also of average length of 5K. The results here are from a uniform random distribution. However, we also ran on a Zipf-ian distribution, whose plots you can see in the paper, and got similar results. All of these experiments were run in parallel across 24 physical, 48 hyperthreads on a machine from AWS with 100 million elements and then 100 million operations. Thank you very much for your time. And in conclusion, the BP tree allows us to overcome the traditional trade-off between point and range operations in the B tree. It enables us to increase the performance for workloads that include both point operations and long scans, and gives us guidance, perhaps in the future, of the benefit of focusing on large nodes to increase the performance of range operations. Also, the code can be found at the link below, and thanks again for your time.